Let's take a look at quadratic graphs and their properties. Our goal today is to graph quadratic functions in the form y equals ax squared and y equals ax squared plus c. Our essential understanding is that a quadratic function is a type of nonlinear function that models certain situations where the rate of change is not constant, thus making it nonlinear. The graph of a quadratic function is a symmetric curve with the highest or lowest point corresponding to a maximum or minimum value. So we'll work through all those different pieces as my phone rings. That's fun. The key concept here, so here's some vocabulary words you're going to want to write down. Some key concept here is a quadratic function is a function that can be written in this form, which should be familiar to you. We've been doing this. Ax squared plus bx plus c, where a is not 0. This form is the standard form of a quadratic function. We've seen this before, where you have the highest degree leading off on the left side, and you go down by degrees. So degree 2, degree 1, degree 0. And this would be in standard form. The simplest quadratic function, f of x equals x squared, or y equals x squared. This is called the parent function. So we kind of always start with this, and it looks like that graph right there. That's what y equals x squared looks like. It creates this U-shaped curve called a parabola. And the thing is about a parabola is that the two sides match exactly. This is called symmetry. The fold or the line that divides the parabola into two matching halves is called the axis of symmetry. So that is right here. So this line is right there. That's called the axis of symmetry, and that happens to be the y-axis. The highest or lowest point on the parabola is its vertex. So highest and lowest point. So these parabolas have a vertex, which is on the axis of symmetry. So it's going to be right there, the vertex of it. So we're familiar with vertex being like a corner of shapes. On a parabola, it is at the bend, at the turning point. Now here's a couple interesting things here. So if a is greater than 0, so if we're looking at this term right here, if a is greater than 0, our parabola opens upward. And that's what we see in our sample here on the right. In that case, the vertex is the minimum point. So this vertex right here communicates to the minimum point, or the lowest point of the parabola. If a is, right here, if a is less than 0, right here, then what's going to happen is the parabola is going to open downward. It's going to kind of invert itself. Like for instance down here, it's going to shift directions and invert down. In that case, the vertex though is the maximum point. It still ends up right there. It's at the tip, at that turning point. So that is still the vertex, but in this case, it's communicating the maximum point. So let's try it on problem 1, identifying the vertex. What are the coordinates of the vertex of each graph? Is it a minimum or a maximum? So I'm looking for the coordinates right here, and that would be 0, 3, and that is a maximum. The coordinate would be this guy right there, and that vertex is at 1, -1, and this would be a minimum. Why don't you press pause and answer question number 1. The vertex of this parabola is at -2, -3, and it's communicating a minimum vertex. You can use the fact that a parabola is symmetric to graph it quickly. First, you find the coordinates of the vertex and several points on one side of the vertex, and then you can just reflect it across the axis of symmetry. So let's look at the parent function. Y equals ax squared. The vertex is at the origin, so the axis of symmetry is the y-axis, or x equals 0. Okay, so let's take a look at this one. So we're going to graph the function y equals 1/3 x squared, and we can see, okay, all right, and we're going to make a table of values. What are the domains and ranges? So here's my d values and my r values. Oh, those actually are my coordinates. So we're going to try it out for 0. So when x is 0, which is 1/3 of 0 squared, we end up with 0. So I have a coordinate at 0, 0, which is the origin, which will then be my vertex. And then I'll try 3. So I want to do 1/3 of 3 squared. So 1/3 of 9 is 3. So I have a coordinate at 3, 3, which is that point. I try 6. So 6 squared, 1/3 of that is 12. So I have a coordinate at 6, 12. And then I can use the information here and go, well, if it's 2 over, it's going to be 2 over, make a dot. If it's 1 over, it's 1 over, make a dot. And then I can create my parabola from that because it is a reflection. The domain is going to be all real numbers because all of those work, but the range is a little bit different. The range specifically is greater than or equal to 0. All right, why don't you grab some graph paper from your packet, and I want you to graph this function and then determine the domain and the range. Why don't you press pause, work out a nice table, and see what you come up with. We can see on this one, it looks like a real narrow parabola. I think it's because my interval that I'm using is 1s, and my 12s completely came off my graph. But I can see that my vertex is at 0, 0. I can see that this -3 caused my parabola to point downward. So that makes my vertex the maximum. And so the maximum is at 0, 0. The domain on this one is all real numbers. Everything works. And my range is less than 0. The coefficient of x squared term in a quadratic function affects the width of the parabola as well as the direction in which it opens. Let's practice this out a little bit so you can kind of see what's going on, what it's talking about. Yeah, let's just try it out. So looking at the graph below, what is the order from the widest or narrowest of the graphs to the quadratic functions? So when I look at this guy, so first of all, I can look at this and see, well, -4, so that's going to point downward. This is positive, so it's going to point upward. That's 1, so that's going to point upward. I can see that the -4, how that's going to affect my graph. Let's take a look and see our choices here so we can just see how it affects our graphs. So -4 is creating a narrow graph. Okay, nice. It's real narrow here. 1/4 positive, so it's pointing upward, and it's a wide one. And then the parent graph, which is positive, and it's by 1s, so it's positive. So the good way to look at it is this kind of this is more of your standard graph, and then it looks like that when your coefficient is further from 0, it's narrower, and when it's close to 0, it's going to be really wide. And that's something to pay attention to. It seems like it should do the opposite, but this is what they do. So it's something you have to train yourself to understand. So of the 3 graphs, this is the order from widest. So the fraction, the parent term, and the -4. So you can see the coefficient is 1/4, 1, and -4. Widest to narrowest. Why don't you give it a try? On number 3, order from widest to narrowest. All right, I'm taking a look at my coefficient. There's the widest. -1 is the next, and 3 is narrow. So as my coefficient gets bigger, my graph actually gets more narrow. The y-axis is the axis of symmetry for the graphs of the function in the form of y equals ax squared plus c. The value of c translates the graph. Okay, so your a term is going to help determine if it's pointing upward or downward. The a term also determines how wide the parabola is, but the c term is going to do something different. The c term translates the graph up or down. So let's look at an example of this. So we can take a look at this right here, and we can already see that it is positive, so it's going to point upward. It's 2, so it's going to be a bit narrow, but the 3 is influencing our graph. So the red shows us what it looks like as just positive and pointing upward, and just by a 2, so that's our red. And then the blue, we now influence that +3 to see what happens. And it looks like it, 1, 2, 3. It shifts our vertex and moves it upward. So the graph of y equals 2x squared plus 3 has the same shape, y equals 2x plus, or 2x squared, but what happened is everything shifts up 3 units. So that's what's going on here. It's doing some shifting. So why don't you try? Take a look at this. Number 4, how are the graphs related? All right, we can see that the graphs are the same here. but the -3, the C term, influences my graph by shifting it down 3. All right, I am going to go and stare at my son's goldfish and see who blinks first.